From Los Alamos National Laboratory, this is the National Security Science Podcast.
You came for an interesting experiment in the sense that we have no idea how violent this will be. Once an explosive shot gets violent enough, for example, if it's a detonation, the pressure produced by a detonation vastly exceeds the strength of all the metals. So what it acts like is when it hits the metal, it just tears it into tiny fragments.
Hello, and welcome back to the National Security Science Podcast, a spin-off of National Security Science magazine at Los Alamos National Laboratory. I'm your host, Brenda Fleming, and we are recording from beautiful northern New Mexico. A high explosives test always sparks excitement. Recently, the National Security Science magazine team had the chance to watch as engineers conducted a high explosives test. National Security Science writer Jill Gibson wrote a story about that experience for our latest issue, and she's here today to tell us about what it was like to watch the experiment. Magazine editor Whitney Spivey and I also attended. It was an exciting opportunity to observe what actually goes on at a high explosives test.
The test took place in a remote part of the lab where scientists carry out these kinds of explosive experiments.
So we're just right up here.
Matt Holmes from the lab's Explosive Applications and Special Projects Group was our guide. So let's dive in and take a listen to what happened that day. The afternoon begins with Holmes driving us out to the location.
All right, come on up.
Where we walk up a set of metal stairs to what's called the firing site. It's a flat, sandy area where the explosion will take place.
Wires and cabling and stuff feeds through. Comes out here so that we can run it to the shot. These right here, you'll see when you go in the bunker, these are our portholes where our cameras are. They all get covered with sand, basically, every shot. But there are cameras right under here, and these turning mirrors let us look at the shot.
After Holmes points out the cameras and mirrors, he shows us the blockhouse.
And then here, this is our blockhouse.
A structure made of huge concrete and rebar blocks. The blocks are topped with a solid steel panel covered in sandbags to form a shelter.
We basically catch all fragments so that we don't start fires. The dead bushes are close enough that we can start fires here every once in a while. So the blocks and everything are to catch the first round of fragments.
Next, we go inside the blockhouse to see the setup. Engineers are gathered around a stainless steel container bolted together, holding the explosive charge. Los Alamos machinists made the explosive charge by pressing and machining small grains of explosive powder.
So this is the actual shot. We have all of this plastic stuff around here with these little black fibers. They're fiber optics for doing PDV. PDV is photon Doppler velocimetry. It's what we use on all of these shots to measure the velocity of stuff, how fast stuff is coming off. Because it comes off so fast that, sometimes it comes off so fast that no other like velocimetry stuff works. So PDV is like our go-to for high speed velocimetry to figure out how fast it is. And basically it's our primary diagnostic. If it comes off really fast, it's really violent. That's what we're trying to figure out. If it comes off really slow and is not violent, that's what we're trying to figure out. So the PDV are these little probes. They're, it's about that far away. They bounce light off of the surface and right back in to the same probe, and then it goes back down below, and we record that, and that tells us how fast, basically, the metal is coming out the probe, at least until it runs into them, and then that's it. We don't have any more.
It's gone.
Yep.
As we look at the experiment, the complex diagnostics in the blockhouse, we ask, what should we expect? After all, it is an explosives test. Will there be a big bang?
You came for an interesting experiment in the sense that we have no idea how violent this will be. Once an explosive shot gets violent enough, for example, if it's a detonation, the pressure produced by a detonation vastly exceeds the strength of all the metals. So what it acts like is when it hits the metal, it just tears it into tiny fragments. It's as if tearing tissue paper, right? Mm-hmm. And so when it's violent enough, it comes apart in itty bitty little fragments. So, and we don't know how violent this is going to be or not. We're not using a detonator, we're using basically an igniter. It's as if you could take like a match, let's say, to the middle of this explosive charge with it sealed all around it so that you've got the match in the very center. That's basically what we're doing.
Why?
Because accident scenarios, anything that you can do that to the explosive accidentally, that you don't intend to do, like design mode detonation, none of those detonate the charge directly the way a detonator does. All of those, at worst, they can give it a thermal stimulus, like a match, like a hotspot. And so all accident scenarios start with a hotspot, and the question is, how violent does it get after you have that initial hotspot? And so this is one of those experiments to see how violent can it get when you start with what is essentially an accident stimulus. So we're not using a match, we're using a laser, and the laser is heating up a tiny bit of like pyrotechnic that goes off, and it's like a little mini blowtorch that spits at the center of the charge.
Holmes keeps emphasizing that the point of the test is all about safety and establishing margins for safety. Like everything that Los Alamos National Laboratory designs, the explosive material being tested has been built to never go off accidentally.
So it's ridiculously safe. And so, but we have ridiculously high standards also for safety. All of our experiments are what's called overtests. It's like you take it, you know, let's say you care about one particular thing being safe. Well, let's make it twice as big. Let's make it twice as confined. Let's make it conservative in all regards, right? And then set that off. And if that doesn't go off, it's a conservative overtest. Then you can say, okay, well, the real thing's never going to go off because we did it way worse case scenario. And so all of our tests, basically, safety tests and explorations, are all these worst case scenario sort of conservative overtests.
Next, the team hooks up all the diagnostic probes and adjusts the mirror system for the high-speed cameras that will capture video of the test.
So what do we have to do before we can fire?
We gotta change this mirror because I don't have enough vertical height to see the top-down mirror. So my thought is we spin it on its edge.
Okay.
So 20. So let's just pick
Stand it up? Yep.
Stand it up and come up with a clever way of holding it.
That's pretty neat, huh?
Okay, I'm gonna need the view rotated up. Keep going, stop. Nice and slow. Keep going, keep going, keep going. Keep going up. Somewhere in the middle of where it snaps back on you. Right there. Leave it there for a minute.
Oh, it's pretty damn good. If he can't see that with his cameras down below, it's because of these mirrors, not that. So I think that's good. If that's secure, are we happy there? Okay.
With everything set up, we join the rest of the researchers in a concrete bunker located beneath the firing site.
You want to come in?
That's where we will all stay during the explosion. Holmes explains that setting up complex explosive tests like this one require a great deal of engineering expertise.
The engineering that I'm referring to is being able to pre-plan and to be prepared all the way up to the last point of like functioning the shot, right? You've designed it ahead of time. You've designed it so it's suited to purpose ahead of time without having to, at the end, modify things because you remember, oh, I forgot about that. I didn't think about that. That didn't occur to me.
Now everyone's in the bunker, and trust me, it's kind of claustrophobic with about 10 people crowded inside making final checks and preparations. The researchers must test every diagnostic system to make sure everything will work.
So what they do is they turn on all the lasers and they check that they're getting an appropriate power back reflection from the PDV.
Okay.
They can check to make sure that it's going to work properly.
What do you think, Bob? Happy with triggering? We'll do one more.
Yeah, we should do like one last.
Yep.
2, 1.
We're doing what's called trigger tests now to make sure that the diagnostics fire that we want to fire when they're supposed to, and they don't fire when they're not supposed to.
Do you want to do it integrated?
Okay, 3, 2, 1, press. There we go. Yeah! That timing should have worked.
Attention all personnel. Attention all personnel. A Plan B series for point 6 will begin in 10 minutes.
Another aspect of our setup is the lighting. In order to see the shot at 300-some thousand frames per second, you have to put in a whole ton of light. Otherwise, it's just black until some light comes out, right? So we have extremely bright LED lights that are up there. So it'll record the shot. When it records a shot, it'll be too fast to see, but then you can play it back.
It's almost time to fire off the experiment. While they make a few more preparations, the team is still discussing and debating what will actually happen when it takes place.
I don't know what's going to happen.
Exactly.
It's very exciting.
Is that normal? Do you usually know what's going to happen?
Oftentimes, we either know what's going to happen or we think we know what's going to happen, even if we're wrong.
And sometimes we're very wrong.
Sometimes we're wrong and we're surprised. But the lead up to it isn't as exciting as when we know that we don't know. This is very much a science test. It's about knowing where the threshold is for dangerous accident scenarios.
Finally, the time for the experiment has arrived. Will it be a boom or a bust?
Firing in 3, 2, 1. Damn. 346. 346. Damn.
Well, balls.
Damn it.
That's a little big.
That's not going to be easy to clean up after.
The sound is deafening. The bunker shakes. The explosion has had much more force than the researchers predicted. But of course, that's why they conducted the experiment, to see what would happen.
Yeah.
It worked.
After the team makes sure it's safe to leave the bunker, we scramble up the stairs to view the aftermath of the blast.
All right, guys. Safe conditions. You want to walk up if you want.
The blockhouse is in shambles. The concrete blocks blown far from their original positions. Some cracked, exposing twisted rebar.
See, it's a bit warm. It's a bit hot. That's one of the shock heated fragments right here.
Oh my gosh.
This is a part where the bolts, you can see the threads where the bolts came through. But yeah, it's warm, it's hot.
Still hot. Oh, it is. It's very hot. The heavy steel roof of the blockhouse appears to have been thrust upward and flipped over. Scraps of nylon are all that remain of the sandbags. Fragments of metal and concrete, still warm from the blast, are strewn across the firing site. An iron girder lies on the side of a slope thrown by the power of the explosion.
Oh, that's a crater.
Yeah. Came through there.
Oh, wow. That is a crater.
The engineers swarm around the site, picking up twisted hunks of steel and pointing out holes where shrapnel pierced the blockhouse roof.
Oh, yeah, I did not expect it to look.
I know. Look under here. There's a big old chunk of that.
Here's your send cut send plate, Thomas.
Yeah,
Beautiful.
it's perfect. We could use it again.
That's-
Put it on the next shot.
That's the
So it's like, well, there's a week's worth of work right there. Just blew that up. Cool.
The good news is the data survived the blast.
Previously, as in, I don't know, historically, results like this were analyzed by this.
That's
You pick it up afterwards and say, that detonated.
yeah.
You know, we shocked the metal, it came apart in small fragments, it detonated. So we now, with PDV, we have diagnostics that let us get a finer distinction.
And that's the next step, analyzing the data and preparing for the next experiments.
So we can focus in on building the next. Yeah, we can do that.
We can build the next
Let's
one.
talk tomorrow and cement this stuff into our brain immediately.
Yeah, PDV.
And that was it. The sun was starting to set when we went home, and the engineers kept working.
What a day. I certainly enjoyed getting to see what this sort of test looks and sounds like.
I agree. Getting to be there was, I have to say this, a real blast.
This experiment was conducted by part of the laboratory called M Division. What exactly does this division do?
The team that conducted this experiment is part of the Dynamics Experiments division. I sat down with Chuck Milkey, who leads the division. Milkey explained that M Division was established in 1945, just after the Manhattan Project, and has been going strong ever since.
So M Division today, we focus on experimental physics and experimental engineering. M Division does these high hazard operations with high explosives. We conduct the high explosives tests at full scale, mostly at the large scale. We focus on our outdoor experiments. Most of the outdoor firing sites at the laboratory, nearly all of them, are within M Division's control and We have the responsibility and authority to run those firing sites. So the outdoor shots are by us. All the large scale shots are all M Division. We'll do large scale outdoor gun shots where we have guns that literally range from 22 caliber long rifle all the way up to M198 6.1 inch or a 155 howitzer. So military weapons to ensure and validate performance under hostile conditions.
M Division also conducts hydrodynamic or hydro tests. These are non-nuclear explosive tests used to study the behavior of nuclear weapons components under conditions that simulate the initial stages of a nuclear explosion, but without producing a nuclear yield. The word hydrodynamic refers to how materials, even solid metals, behave like fluids under extreme pressures and temperatures.
The way I like to describe what a hydro test is like you really got to understand where that fits into the picture of weapon certification. So I'd like to think of a pyramid, okay, a three-dimensional pyramid, where at the base of that pyramid you have a great number of building blocks that support the weight above it. And those building blocks are small-scale physics experiments. Those small-scale physics experiments are aimed at understanding the properties of the materials, the properties of the explosives, the interactions of the materials and the explosives, and all the things, and again, the hundreds of different types of materials that might go into a modern weapon today, be it nuclear or conventional. There's a lot of parts that have to work in concert together. So those parts have got to be all independently tested and verified and validated because of the position that with nuclear weapons testing today, that we have pivoted since 1992. We do not do full-scale nuclear yield experiments. So in order to underwrite those experiments, we have to understand the complex response of materials in a full regime of the environment that the weapon has to operate. Another dimension to that problem is aging of the materials. Understanding how materials responses to aging is something that requires a significant amount of testing and verification validation. And then taking those data and then giving those data to the designers and the modelers that can create models from that data, give those models to the designers that can use those models in their weapons codes to simulate the nuclear weapon functioning in its full capacity.
Milky says one of the most crucial aspects of working with high explosives is ensuring safety, which is why M Division conducts a wide variety of high explosive safety tests. People in the division also handle large amounts of high explosives, assembling experiments and machining explosive material that looks like tiny pellets into parts and shapes. The division machines thousands of high explosive parts each year.
Safety is a extremely important thing when it comes to nuclear weapons for the United States, especially nuclear weapon assembly. The folks who are assembling those weapons are handling large charges of high explosives. And, you have to lift those charges out of a box, carry it some distance, and then place it onto the components in the weapon. So that handling of HE is what I view as, one of the most significantly important and dangerous aspects of the work. Modern high explosives have a large range of sensitivity to insult. By insult, I mean dropping or heating. Always treat all high explosives the same, with great respect, not with fear. Risk comes from handling high explosives. When you have a high explosive sitting on a shelf, undisturbed, it is completely safe and not dangerous. In most normal cases, when that HE is sitting on a shelf, it is completely safe. When a human being picks it up, and if you mishandle it, if you drop the high explosive, what happens is that when that high explosive makes impact to a surface, it depends on what that surface is. It's a very large amount of HE handling. HE handling is that human HE interface, and that is what makes high explosives dangerous, if you will.
M Division also studies how shocks from detonation impact high explosives and other materials and conducts other tests and experiments that support national security.
It's a relatively small number of people in the country that make multiple sacrifices at different levels to assure that our nuclear deterrence is the safest possible, most effective, and most reliable nuclear deterrence. And the tests that we do are essential to assure that nuclear deterrence.
Thanks, Jill, for sharing that broader perspective. It was a great example how engineers at Los Alamos National Laboratory are working hard to ensure that better science equals better national security. Many thanks to Chuck Milkey, Matt Holmes, Michael Erickson, Thomas Macumber, Dennis Jaramillo, as well as everyone else from the Explosives Application and Special Projects Group who helped explain what they were doing and put up with a few more extra people in the bunker during the tests. You can read more about engineering at Los Alamos in our latest issue of the National Security Science magazine. And thank you so much to you, the listener. You can find more at lanl.gov.